This function here, vector init default, is what we started off by talking about. It sort of initializes the memory. So we have, first of all, we declare a variable p vector, which is a pointer to a vector, meaning it keeps the address of a vector, basically pointer to an instance of a vector it is. We assign the memory to it. We check if the memory is available. If it is, then we allocate, we initialize the capacity. We set the number of items to 0 because at the beginning there's no items at all in the array. And then over here, we allocate memory for the array. We check whether the memory exists. If there's no memory, then we free our vector because our vector container, because we no longer need it because we are keeping the items in the array. So if you cannot make the array, then we do not need that. And then if it's successful, we return this particular pointer. Okay, we return it. So we are returning, this function is returning a pointer to a vector, which is what we want to use in main up here. So initially in main, we just basically have a p vector pointer that we declared, initially null, and then we use the vector init default function to initialize it. So that's what the initializer is doing. Then we create a function, for example, with the push items function, which is basically pushing items into the array, and it's pushing items one by one. So we pass the pointer to vector, and then we pass an item, and then we allocate those items one by one. We have another function, print items. It prints all the items in the array. And we also created another function called destroy that is freeing up all the memory contained in the or held by the structure. Okay, so that's where we were last time, and we said there are a couple of things. There are more things that we could actually do. One of them is this function here, push items. Currently, the push items is basically pushing items one by one till the size or till the capacity, okay? Till we fill up the array. But the idea of us creating this vector is to create a dynamic array. Now, what do I mean by dynamic array? I mean an array that keeps growing as we add items into it. Okay, so is there somebody who can tell us how we can end up achieving that? Can put that on the chart. Is somebody who can tell us how would I go about adding, making sure that every single time I push items into the array, that basically this will keep growing. That my array will keep growing. Let me see whether there's anything on the chart. Okay, there are a couple of things on the chart. Okay, allocate more memory. Somebody says allocate more memory, increase the capacity. So actually that's a good point, yeah? Increase the capacity, because increasing the capacity means then that we are able to add more items. But again, the other answer, allocating more memory, is also good because it goes hand in hand. If we increase the capacity, then we must as well extend the memory, because, well, just saying that memory is equals to, +1 or +2 or double the amount without increasing the memory does not help. So we could do that. So I could come up here and say I'm going to increase the memory. So look at this. This says if p vector number of items is less than p vector capacity, which basically means we are checking whether it's empty or not, right? Correct? Yeah, we are checking, basically here we are checking whether the array is empty or not. P vector, well, it has, whether we have enough room to add items, yeah? We are checking whether we have room to add items. We are saying if p vec number of items is less than p vec capacity, meaning that the array is not full, then add items. So we are starting to think about what about the case where the array is actually full? One of the things we could actually do, we could come up here and create a function that checks whether the array is full, so that we don't keep doing that, right? You know, we can check whether our array is empty. So we can check whether the array is empty, okay, or is full, or something like this, right? Okay, so how would we go about that? So this function would possibly return for us something to tell us, you know. So it should be able to return for us maybe true or false. Okay, if we created a function that's going to tell us whether our array is full or not, then that array, that function should return for us true or false. Now, I want the array, I want the function to actually receive those words, true or false. So what can we use to create something that returns for us true or false in those, you know, well, programmatically, it's going to be either 0 or 1, but I want to write the words true or false. What can I create? Someone put there, if statement. I want just something that can write for us true or false, like that describes just those two words with nothing else. But yeah, enum. A lot of people have said enum. Yeah, I'm looking for an enum, right? So we can create something like this. I'm going to use the type dev facility, type enum. We're going to call it bool for Boolean. And what we're going to do is we can say false to mean 0, true to mean true for 1. And then because we're using type def, we can rename this to maybe something like Boolean, like this. Okay. So let's save this. And now our function should receive this, should return this Boolean. So I want to return Boolean here. And then maybe I can say is full. Okay. You know, we can call this is full, this particular function, whether is full. Okay. So given a p vector, this guy here, given this, I want it to return whether it's full or not full. All right, so we can copy this. I'm going to save this. And we can go to the implementation, and I want to paste it here. And this is going to be an easy one, right? So I can actually copy this code here and say, well, if p vector number of items is less than p vector capacity, what should we return there? If p vector, well, it's not full, right? So it's not full. So maybe we return false, meaning that it's not full, right? It's not full, false, it's not full. Otherwise, we can just return true. That's what I meant by returning the words. Well, this is just basically masking them, right? Because the false means 0 really, and true means 1, because we're using an enum, and we know that the enumerators are integers, are integer constants. So we are really returning a 0 or 1 in this particular case. So that's good. So we return false or return true. And in here then, we can say, well, if this is false, if not is full. So what I mean with this is immediately we come to this push items function, we can call this function here. And if this function returns false, right? If this function returns false, then we can add items, correct? The other way of looking at it is if I was to remove these things here and put them outside here, the way I've done, then we can say, well, if it's full, what shall we do? If the array is full, okay, this block of code should run. Okay, so what I'm trying to do is that if the array is full, then I want to create a block here, a block of code in here that should execute before we start adding items into the array. All right, so someone to tell me, there's something we have learned before when we talked about dynamic memory allocation that can help us extend the array. If we, extend the array, someone to write in the chat, what is it? It's a facility that we have used. Realloc, people have said realloc, yeah. So we could potentially use the alloc. So let's use the alloc. So our array is pvec data, like that, pvec data. So we'll say we want to extend this. So remember, we want to call realloc. Realloc receives two arguments. The first one is the pointer, the one that we want to extend the memory of. So we can say pvec data, like that, pvec data, and then the other argument is the amount of new memory. Yeah? What is the total amount of memory will the new array have? So someone to write for me, what would that be? How big should that be? So remember, normally, if you look at malloc up here, malloc just says to us, well, we want to say 7, the capacity multiplied by the number of bytes used to store an integer in this particular case. So if we want to extend this, okay, we basically want to create a new block. And then automatically what realloc does is it will copy the items from the old block into the new block. So, well, number one, I should have something like this, pvector times size. This is the amount of memory that we currently hold. We currently hold pvector capacity times size of integer. That's the number of bytes that we currently have. Okay, so how many more bytes should we add? How many more bytes should we add? To the new array? Well, it depends on the number of items that we are adding, okay? As some people have said 4, however many items we are pushing. Okay, good stuff. I like the way you guys are thinking, so that's correct. However, vectors by design, okay, they double the amount of memory, okay? They double the amount of memory by design. So what we need to do is take these things here and multiply by 2, like that. So we are doubling the amount of memory. So this we know, this will work fine, okay? This will work fine. Now, we know also realloc returns for us a void pointer. So we want to typecast this back to an integer pointer like this, so that now our realloc basically gives us an integer pointer, or the memory that's basically given by realloc is basically reserved for keeping integers. That's what we have done up here. Well, the problem, of course, with realloc, as we saw before, is that realloc, just like malloc or callocate, they can also return null, okay? But the problem is, because of the way it's set up, even if it was null, meaning that there's no memory, there's no way for us to check this pvector data whether it's null. There's no way to check it because these will contain the memory, the old block. Okay, so let me try to get a pen and write a little bit about what is happening here. So when you call the alloc, so supposing our pvec data looks something like this. Let's say our pvec data is this block, is looking at this block, and this block has 7 items inside of it. When we do realloc, what realloc does is initially it tries to check in the memory whether there is enough room to add to this. So it tries to check whether there's enough room there. If there's enough room there, then it just extends the array. which basically means we have the old array or the items in the old array extended with our memory extended. If this memory is not there, it will go in and create a new block. To go in and create a new block. So let me remove that. This is now the second instance. So if the first instance, if there's no more memory to be extended up here, it will go and create a new block like this. It will copy the items here. So supposing we had 7, 6, 8, 5, 1. It will go copy this data now. 7, 6, 8, 5, 1. And the memory, and extends this. And then it will free this. And our P vector data is pointing to this. Now, if there's no memory at all to either create a new block or to extend the old block, it will return null. But it will return null, but our P vector data will still be pointing to the old block. So meaning that we can't really test it to see whether there have been a problem. Okay? So, well, it will still work if the memory was there. It will still work if the memory is there, but that's the scenarios that we are likely to face. So one of the best things to do with this, instead of using realloc, is to be explicit and use malloc. So malloc will work the same way. We'll just create a new block. We'll just create a whole new block. So the old block will be, so let's imagine that this will be our P vector data, pvec data. This is pointing to this block here. Supposing this block has some data, as we had before, 7, 6, 8, 5, 1, for example. So if we use malloc, we'll create a new block here. Let me get up an eraser. We can create a new block here. Let's imagine that we call it new data block. And what we'll then do with the new data block, we shall copy this material 76851, which we have done here. We shall copy this, and then would free this and point the P vector data should point to this one. So let's try to do that, program that, and see how it would work. So we don't want to use that because of the reasons. We don't want to use the realloc for the reasons that I mentioned before. So, but what we could do, we can create a new pointer. We call it new data. So this is going to be like a pointer to a new array. A pointer to a new block. Okay, we'll say this is equals to null initially because there is no, we have not assigned any memory. Then when we realize that our array, our old array is full by calling this function, then we create new memory block. So I'm going to do that here. Remember, we want it to be double the size, just like this. So I'm just going to change this to malloc, and this is going to be our new data. So now we have created a new block. Because we have used malloc, we can check whether this has returned null. So we can say here, if new data like that, if new data is null, meaning that we don't actually now have memory, then, well, that means what that means. This means we do not, this means a new array cannot be created, and therefore we cannot add items. Right? So if we created this would mean that a new array cannot be created, and therefore we cannot add items. Well, basically that tells us that our push items function should be returning something. Correct? I mean, if we are not able to make a new array and therefore we are not able to add items, remember this function is to add items. If we are not able to add items, then this function then should return or should tell the user that we were unsuccessful in adding items. So maybe we should return something like success or failure. What do you think? Let me know your suggestions on the chat. Yeah, so because there's no way to do that. So maybe what we should do is create another another enum here. We're going to call it type def here. Maybe we say enum. We call it something like status. It should tell us the status of our work, right? And maybe we can say failure, success, and maybe we'll rename this to status, something like that. So our function in this case is going to be returning a status that tells us whether we are successful or not successful. Okay, so that's what we're going to try to do. So now, instead of returning void, instead of this function being non-value returning function, let's return a status which tells us whether we have been successful in adding items or not. So if new data becomes null, then we can say, well, return failure. We are returning failure because we were unable to create a new memory block, which basically says that we cannot be able to work with this. All right, so that's number one. Let me move this in a little bit. Okay. The other thing is now, supposing now a new memory block has been created, then we should do this now. We should copy these items from the old block to the new block. Okay, from the old block to the new block. We can just put an easy for loop for int I equal to 0, I less than maybe the total items that we are there. I think we call that p vector. We can either go to the capacity because the capacity is still the capacity, or we can go to the number of items. Did we call it number of items? Yeah, number of items. Okay, so int I equal to 0, I less than p vector, number of items, I plus plus. So these then would copy items for us one by one. And then, so new data at I should be the p vector. What's p vector or p vec? P vec data. So remember all these things, we call them p vec. We are using this p vec here, p vec here, sorry, p vec. P vec. So what we want to do is p vec data at I, and that should be able just to copy the items just one by one. So that's what we have achieved. We have copied these items into these new memory blocks that we created. Then we can free the old block now. So we can say free p vec data. Now, how does that mean? It means go now to this block here and just delete it off. Now, remember, the free function will then set this p vec data, the pointer, to null. So this vector now is not pointing to anything. This vector now is pointing to null. Sorry, this pointer is now pointing to null after we have called this. But because our vector, the structure, has in it this pointer called data and not new data, then what we should do is point this to this one. So the next line of code we can do is we can say p vec data is equals to new data, which basically is we are just pointing to this. Okay, now do you see that? Do you see what we just did there? So we have created a new block copied the material from the old block into the new block and freed the old one. Just exactly what Rialo could have done, but the only idea here is that we have been able to do that and being able to also check if malloc returned an error or not. Now, who can tell me what next we do? Now that we have been able to copy data to the new block, so we have a big block like this, what other item has been affected by our work? What other thing has been affected? What other variables got affected by us being able to build this new memory block and allocating the or assigning the pointer to there? Which other one? Capacity, yes. So remember here, now the new memory block has twice the capacity. So we should update our capacity. So we possibly should come in here and say pivot capacity. Should come up here and say the capacity. Once we have done that, then we can add items. We can increment the number of items, and maybe also now we can return success. And we can save this. Are there any questions for me on this? Are there questions for me on this? So what we have worked on is this idea that we want our array to double the amount of capacity as we go on, as we add items. We could test this as you type your questions. Well, for the case of vector, yes, we want to double the memory. And I'll show you why that we need to do so. Remember, important thing here is this. Every single time our array gets full, we do all this stuff. We create a new block. Every single time our array gets full, we are creating a new block, copying the amount from the old block into the new block, right? So if we decided not to double the memory, but to just add one byte, add enough memory equivalent to the item that we are adding, then we'll be doing this the whole time. We'll be making a new block, copying old material into the new block, right? Freeing the old block and doing that all the time, which consumes time to do that. It basically means that we have to keep this n amount of time, where n means the new additional items that we are adding to the memory. So in order to stop doing that, if we double the amount of memory, it means we have now capacity to add more items without having to copy things back and forth. So that's why we are doubling the memory. Sure. Okay, so far so good. So let's see whether this works. Are you satisfied with that answer, by the way? Okay, good. So let's try to do this. I'm going to clear this. So this class is vector 204. Okay, so these are our files here. So let's make sure that they are all sort of saved. Okay, so this has been saved. And the vector.h. Remember, we just changed push items here so that it can return status. So maybe that's an important thing to do. And we have done it here as well. And we have done this as well. So we are hoping that, remember when we stopped last time, we could not be able to do this, right? We could not be able to, we only had 7 items, so we could not be able to add these new things. That's where we stopped. We could not add new things. So we are trying to see whether it can add these things up here. So if we start by 7, 1, 2, 3. So let's print here actually. Why don't we say print F, and we print items. Okay, capacity is, supposing we do that, capacity you can say capacity is that, and items, number of items is, okay, and then we can try to say p vector capacity and p vector capacity and p vector number of items, I think, number of items. So these are the things that we have. And I'm going to copy these, and I'm going to paste it here as well, you know, so that we can be able to tell whether we are doing some stuff, we are doing the correct stuff or not. Okay, so let's save that. I can try to run this now. Remember, we're going to use GCC wall like this. And we have a couple of files, vector.h, vector.c, and we have main like that. Okay, let's try to see whether it compiles with no problems. Okay, compiles, no problem. So remember, if I do something like this, if I list all the files, you'll see that file, the out.file up here. And this out.file is our executable. So I can run this like that. And well, we have these items here. So in the beginning, oh, maybe I should make new lines. So it becomes chaotic. Let's add new lines in here. All right, so I'll add new lines like that. I will try running this again. Compiles, no issues, runs the file, and it tells me the capacity is 7 initially, and we had number of items being 6. Then that's basically up here. So we added 1, 2, 3, 4, 5, 6. We added 6 items. So the machine told us the capacity is 7, and we have added 6 items. Then we added 2 more items, which basically meant that the array should grow, because to get full and should grow. When we call that, it tells us the capacity is 14 now, and number of items is 8, because we have just added more items, 2 more items. We added 2 more items, so it grew with 10, and the capacity stayed the same. So we do not have to call that memory block for when the array is full again, until, if let's say we added another 6 items here, say we added another 6 items instead. So if I run this, and write it out, now our array started with a capacity of 7. We first added 6 items. We added 2 more items. So our capacity grew to 14, doubled the size, and we had 8 items. Then we added more items. Our array then doubled the size to 28, and we had 16 items. So we don't have to call this memory block here, this here, when the array is full. All this work, look at the work that needs to be done. This is a work that needs to be done when the array is full. So we are avoiding to do this by ensuring that we double the memory. But this works like a dream, it works well. Now, for the purposes of your learning, either for doing your labs or implementing these kind of things, it's important to understand how this function, the init default function, how it works, the way we described it last time we met. This function that we have just created, and even this function, the destroy function, you're going to see these things a lot, so it's important to understand how they work. Similarly, whereas these print items is not too hard, it's important for you to understand how to do it. Similarly, here we made a new one called is full, which was checking whether the array is full or not. So that is good. Maybe we can make even one more, like we can make one more function that basically will return for us, given an index, it should return for us the item at that index. Okay, so given an index, it should return for us an item at that index. So, well, if it's going to return an item at that index, then it should return an integer because the array in this case is keeping integers, right? So it's returning an integer. So we can say, let's call this function pop item. Well, I don't mean pop in the concept that it's going to remove the items for sure. It's basically just going to report for us an item at a particular index. So I can copy this, it's going to look the same like this. So I can copy this, I can paste that. Remember, I'm just creating anything. And you should be able to also do the same. So this is going to return an item, given an index, return an item, given an index. So that's what it's basically doing. So then we can implement it. Okay, I'm going to save this. I'm going to copy this material here, and we can try to implement it. Okay. All right. So why don't you implement that? I'll give you 3 minutes to actually implement that, and then to implement that, and then we go on with it. Okay. Take us some time. Try to do that. Okay. Tell me what we need to do. Okay, so we want a function. This function is not really popping an items, like removing items. It's basically just reporting for us. Okay, here, maybe I should write here. Here, the meaning of pop is not to remove item, but to report what item is in the given index. Someone to paste their code. What do you think we should implement this one? How shall we implement that one? How shall we implement this one? Well, if we were to check whether an item exists in a particular index, yeah, if we were to check whether an item exists in that particular index, what's the first thing we should do? What's the first thing we should do? What's the first thing we should do? Well, we actually have a variable that's keeping track of the index. What variable is that? Yeah, we have index. Index is where we actually want, it's a place in the array that we want. There's something I'm looking for. What should we look for in the array to ensure that we can actually report an item? Well, make sure it's not null. Well, remember it cannot be null, right? Because we already, we could check whether p vector data is null, but then we would think that those things have already been taken care of by functions like like our initialization function. Remember, our initialization function is the constructor, right? It's a constructor. It's already constructing for us all these things. So we would ensure that they are there. It's already been done. Yeah, so, well, okay, so the last item of the array, rather, check the last item of the array. Well, we should, I think all of you have some sort of suggestions which could be good. We should first of all check whether the array has items. Imagine we are asking for the array to give us, an item at a particular index, and maybe it doesn't have any things. So we should be checking whether the array is empty, correct? Because if it's empty, then we do not have something to return. How would we check that the array is empty? How would we check whether the array is empty? Compare with the number of items, yeah. So we could say if pvec number of items, if it's 0, right? Maybe I should even say, just to make sure, well, this cannot happen, like it can't be -1, but just in case. If number of items is less or equal to 0, meaning that we do not have any items, right? Then we can return, maybe, I don't know what to return, because it means that the array is the array is basically empty, right? It would mean that the array is actually empty. So maybe we can say return, maybe we can have a special number. I'll just write a number like that. We are return a special number, because array is empty. Otherwise, return maybe pvec data in that particular index that is required of us. So it's not complicated. We have been given an index. Give me the item in that index. So in this case, if I'm given index 5, I can go and get it, right? We can actually also check we can compare with the index, right? Whatever index we have been given, because it's possible, but it's possible that we might have items, but we have been passed an index here that is greater than the actual total number of items that are there, right? So I actually think that's a very good point. It's a very good point. Instead of checking that the array is empty, compare this with the index, right? So how would we rewrite this to compare with the index? So I think in this case, we could just say if if the number of items is less than given index, then basically we can report this number here, because it would mean that we do not have enough items, right? Correct? Otherwise, return the item at that particular index. I think this is a more correct assumption of it. So this is good, and we can save this. There are other functions that we could write, go write them, helper functions, what we could call, helper functions. So remember, what we want to achieve is, instead of us being able to call capacity and calling the number of items, we should make this to be such a well implemented structure that we have functions that tells us information regarding capacity and number of items. So I could have something like says int get number of functions, get vector capacity, get vector capacity, which given a particular vector, pointer to vector, like this, should return for me the capacity. That should return for me the capacity. And I can also have another helper function. These are normally called getters, by the way. Get vector items. Get number of items. given this, tell me how many items are in the array. So instead of me calling, checking this directory, I can also hide that implementation by not doing that, but getting this, get vector items, get vector capacity, so that nobody actually knows, nobody actually knows what my variables are called. This is what this achieves. So these ones are easy actually to do. So I can just copy them and we can go to our implementation and we can paste this. And here we can just say, return pvec, capacity, right? Easy peasy. This one. Return pvec, number of items. So these are just helper functions, right? And well, the good thing about them is instead of me, so let me just copy this. When I'm in main, imagining that I did not know, let's imagine that I did not know the what the struct contains, what the member variables are called. Instead of that, I already have this API that tells me that I have a function called get vector capacity, get vector items, and I can use it instead. So instead of saying p vector capacity here, I can just say get vector. I can just use this instead. Get capacity. Similar here. I can say get items. Maybe I should have said get number of items. Get number of items, and then I can just pass p vector like this. So let me go and back and check that. So I can get the number of items now. I can get number of items and I can get my capacity. So if I go back to this one, that's what I'm doing. And now I do not need to know what the member variables are being called at all. I do not need that. I just need a function that exposes them to me. Okay, so I can hide this. I can save that. And I can try running it again. See whether we have forgotten a semicolon somewhere. Nothing wrong with it. And we can do that. And everything works fine. So far, so good for everybody? Questions for me? Questions for me? Awesome. So that's good. So let's go on. So now, what we have described and what we have written so far is really a full implementation of what a vector data structure would look like. Now, what does that mean? This is the structure where our data will be contained, and these are functions, okay, and other declarations that would help us to work with that particular structure. We say that this file, the vector.h file in this case, is the API, is application programming interface. And the idea is we would be able to give, or what we expose to the user of this is not the vector.c or main vector.c. We would give them this, right? The .h file, and they can be able to include it in their main and be able to work with it. So the most important thing to actually understand is that what we are learning here is how to create these kind of objects so that others can be able to use them, or ourselves can also be able to use them. Now, well, these things here also I don't want, so this exposes, for example, enum bool, enum status, all these things are also exposing information that might be important not to expose. So I can cut this, And what I'm going to do, I'm going to create a new file and I'm going to put them there. I'm going to save this file. And because it basically just describes some work, I'm just going to call it status.c file. Sorry, it should be status.h. Okay, so this status.h file. Okay, so we have our status.h file over here. Uh-oh. Okay, okay. So this status.h file here. And we are going to guard it the way we guarded the other stuff with the conditional with the conditional preprocessor directives. So if I go back in here, I can just guard it. I'm going to call this status underscore h. Remember, this is just the name of the macro. So status underscore h, and then we add if. So what I'm trying to do now, I'm trying to limit as far as possible. Yeah, I'm trying to limit as much as possible my implementation now, right? I'm trying to make sure that in this implementation that we have, okay, that in this implementation that we have, that as so as much as possible that this implementation that we have is actually as hidden as possible. So everything now should work still fine. And what we'll do, this status.h file, we're going to include it into our vector.h file over here. So here we're going to say include status.h. Remember, I don't have to actually, because the main file that we are working on is the is the vector.h file. I do not need to include status.h file here. Neither do I need to include it here. It should be able to be picked up with no problem. So now, if we run this code, so let's go back to vector.h to ensure nothing is there. So everything is fine. So now if I come back, I try running this, run it, nothing, everything looks very, very good. Everything is fine as well. So that's all what we needed to do. I want these things to print out nicely, so that's what I was trying to play around with this. Maybe I should just put 5 or 6 here. Okay. So far, what we have achieved is actual full implementation. Okay, is an actual full implementation of what the vector is. That's the information that we have. Okay, now the next 15 minutes that we have, we're going to speak about a concept called opaque object design. Okay, so that's what we're going to be speaking about. Opaque object design. All the best, Ethan. Just make sure that you check the opaque object design stuff that I'm going to be speaking about now.
All right.
Yeah, all the best. If you look at this file now, we have sort of hidden most of our implementation, right? Remember, this file, the API is hiding the implementation. The implementation is basically here in this file, but we are not exposing this file at all. But the major here issue is people can still see this vector. They can see the array, they can see the capacity, and they can see the number of items. So whether or not I have the get vector number of items, get vector capacity, which I am using in this side, well, giving this to somebody, they'll still see what the structure is. So I would like to hide that. So what do I mean? I would like to take these like this and cut it and paste it up here in my implementation that nobody else will see. You see that? So I want to make sure that everything still works, okay? I want to make sure that everything still works. So we're going to check just a couple of things to make sure everything still works. Now, look, Now we need something that mimics, we need something that mimics this, because all our files, all our functions need the struct. So now look at this. So the next thing we're going to describe is an opaque object. So we're going to imagine that we have an object which is a void pointer. It's a pointer to anything. So we are going to call this maybe vector. I'm going to, so that we change the other things on the other side. So I'm going to rename the void pointer and call it vector. Now, I don't get confused, so follow with me closely. I know that I can mask anything using a void pointer, okay? Because a void pointer means a pointer to anything. When a pointer points to null, it basically means it's pointing to nothing. But when something is declared of type void star, it means it can point to anything. That pointer can keep an address of anything. Now, going with the same concept, I'm going to say, well, I have an object called vector, but this, remember, the typedef facility is just renaming. So we are renaming typedef to mean this. So wherever I had vector star, I can just describe this as vector. So I'm going to remove these things here now, because vector, the name vector in this case, refers to the name vector refers to the void pointer here. So I removed one star here, as I would going to do here. I'm going to remove just one star because the vector itself here, this is as the same as saying this. But okay. So pvec is pointer to a pointer to a void pointer. So in the same regard, instead of having this, I'm just putting this word here, vector. And this was just taking a vector, so I'm just going to remove it here. So now what is happening now is we have transformed ourselves not to the old type, but to something called void star, which is pointed to anything. So somebody seeing this does not know what is a vector reading, because what they see is a void star. All right, so let's save this. Okay, so if you have questions, please have them in mind. Now, when we go now to our .c file, this is where a true implementation is. I'm going to say that this is the known type, the known data type, because the other one is unknown, okay? An unknown type, data type. This is masking the known type or hiding the implementation of the unknown type, okay? This is an opaque object. It's an object that we do not know anything about. It's an opaque object, okay? And if you were to think about matter when you're in grade 4, then this is basically to say that this is the transparent object, okay? Now, we know it's a known data type, and we have renamed it. We are going to call it vector. But because we don't want it to have problems with the known vector, allow me to rename this to something like my underscore vector or something like this, which is basically a known one. So I'm renaming this to my vector. So whenever I had vector here, because we know now this vector is being used somewhere else, I'm going to, the function is returning a vector, but here we are using a my vector. So this p vector is of type my vector. And wherever we had vector in here, I'm going to call it my vector, because that's the known type. So all these things are good. All this is good. All this is good. But then here, when we return, because we want to return a vector type, we are going to typecast it to a vector type. Remember, p vector is a type of my vector. but I want to return vector or a void star. So I'm going to return it here. I save that. Similarly here we are getting something of type vector. That's what we described. So I must change this to that type that we know about. So why would I do it? I'll just typecast it. I'll just do that. I'll say, because we were using pvec here, I'll just say this. Pvec is equals to typecast this, pvec, which is of type vector, typecast it to my vector pointer. So I'm going to carry this, paste it here, and I'm going to write here pvec. That's all. So these now will transform this type of vector, which is a void star, to a my vector. And then it's going to be used the whole place here. I don't need to do anything. Similarly here, remember this p vector is of type vector. I need to first of all transform it to a my vector so that it can be used. Similarly here, I need to transform that to a my vector so that it can be used. Similarly here, I can just remove this and I'm going to paste that. So again, transform it. This one is a Boolean, it's receiving that. I can do that. Should work. And here we are printing items. So it was receiving a p vector, which is a pointer to a void star. So when I'm transforming it here, which is almost like what we did before, the only difference is, so actually here we are receiving something called p vector. The only difference is I'm going to have this star p vector here. Sorry. Okay, and the destroy one should also look like this. So I'm going to paste it here. And I'm going to remove one of these. Okay, so everything now has been sort of, by just doing a typecast to the known type, we are basically just using the same thing, only that we have brought in the known type inside and it's being hidden by the opaque type that we created. Okay, by the opaque type that we have created. So that would look like that. Status does not change. This one does not change. Let me just save it because everything stayed the same. In the main here, we are creating p vector as a pointer to a vector. But because this has now become void star, we can just remove this. And our function vector init default really returns a vector. We know that because we just implemented a so. It returns just a vector. So what we have done will still work in main. The other functions also, all of them get p vector, print items does that, and should be able to work fine. So let's save all this now and see whether this works. Okay, so let's get this. Okay, feedback number of items. I think there's some problems. Too many errors omitted. Pivec. Did we put something else? Okay, it doesn't want the same items named the same. That's what basically is happening. So we might as well try to change the names somewhere. Okay, so let's go back and quickly possibly be able to do that before we go. So it's up here. This one will not have a problem because we are not renaming anything. Here we were getting pvec, and this pvec we are using here. So maybe let's just rename this to p vector like that. Okay, let's rename this just to p vector like this so that we don't have any particular problem. Okay. This one the same. It's going to be called p vector. So remember, you know, because these are variables. Remember, the stuff that goes into these parentheses, they are local variables to the function, and also the things we declare are local variable to those functions. So that's why we are getting an error, because they are in the same functions. We can have two functions, two variables in the same functions with the same names. That's what's happening there. Okay, so similar here. There. This one, I think this one did not have any problems, and these ones did not have any particular problems. Okay, so we can save this. Maybe if we go here, we can also rename them just to make sure that everything is started. Similar here. Here, and we can save this. Okay, that's good. And this is good. Okay, so let's try it one more time and we see what happens. 1 warning and 6 errors. P vector equal to null. Address of P vector. I think we are getting somewhere. P vector, my vector. What is this? Vector C115. So let's debug this quickly and then we can go. So I think it's somewhere 115 here. So, oh, sorry, we had something called P vector here. Sorry, that's P vector being named up here. And this is still good. Yep. Okay. Yeah. Okay. So P vec here. So that's correct. We should be freeing P vec. And here we should also be freeing P vec. And we could stay here. If this P vector here, we could just say star P vector, which is basically that one, is equal to null, because we have renamed everything else. Okay, so we save these guys down here. We run it, no problem now. So if we clear all these errors, please re-watch this so that you can see how I debug things, right? Okay, now if we run this, does the same thing, works like a dream. Okay, so I am going to add there. Okay, I'm going to add there now. Then we have basically learned how to do opaque object design using a vector. Our file, this one now, vector.h, which is our API or blueprint for the data structure, the blueprint or API for the data structure completely masks any implementation. It completes masks any implementation of our structure. Somebody seeing this file does not know how our vector has been defined or how it looks like or what the member variables are contained in it at all. That's what opaque objects do. So vector here is an opaque object. What we may have done in main here, instead of declaring this as a P vector, because really this is P vector here as defined here is this is void star down here. So the term vector there means void star. So instead of calling it P vector, we possibly could have called it H vector or a handle, you know, or an opaque handle. This is an opaque handle. Opaque handle, which is basically a pointer that, okay, you know, a pointer to an opaque object that masks the or conceals the known data type. So this is basically a handle. It's basically a handle to it. So we could use that. So in this case, basically this would be H vector that's being returned. We could talk about this being H vector here, H vector, H vector, H vector, and we could pass that as H vector here. Similarly here, we can call it this H vector, and we can call it H vector. There are many things that somebody could, oh look, all these things will need to be changed. So I think we can just find replace, and then where we have P vector, we just say H vector, something like this. So that will sort that out. And so that will sort that out. And maybe here, because we are passing a pointer, really a pointer to the handle, so we can say pass the pointer to the handle. Similarly, maybe here we can say pass the pointer to the handle instead. So I'm going to call that PH vector because we are passing the pointer of the handle. It's not a big deal. I mean, we just need to change a H here and a H here and a H here and a H here and maybe another H here, and we'll be done. Okay, and so this would be we call this P vec really. So this should have been a P vec up here as well. Okay, so we can save everything now. Save everything this side as well. Save everything that needs to be saved, and we can run this. Okay, no problem. We can A dot out, and everything works right at home. So I'm going to stop there now. Okay, and we will be able to discuss linked list next time.